In this video, I will introduce the geometry of statistical feature learning in mean-field Langevin dynamics. This is based on a paper joined with Tomoya Wakayama, Guillaume Lecué, and Taiji Suzuki. All of you have seen the empirical success of neural networks in different tasks. Now, let's try to build a theory for neural networks. Arguably, the most important problem in neural network theory is feature learning. The study of feature learning aims to answer the following two questions. 1. What features are learned by training the neural network? 2. Why do these learned features improve estimation? To answer these two questions, we need to place ourselves in the framework of stats learning theory. I assume you are familiar with the supervised regression framework. In this framework, the objective is to learn an unknown function f star, which is also called the signal. It is a function from Rd to R. To learn this function, you are given by n training samples xi, yi, and they are independent copies of the input-output pair xy, and we denote the distribution of the pair xy by the probability measure p. Here, the marginal distribution of x is denoted by px, and y is defined by f star of x plus the noise, where the noise c is independent with the design variable x, and for simplicity, we assume the noise follows the Gaussian distribution with the variance sigma c to the square. So a statistician constructs a functions class f and an estimator f n hat, such that with high probability with respect to the distribution of the training samples, the L2 norm between the estimator and the signal to the square is small. To really compute this estimator on the computer, we need to specify the learning algorithm. So a learning algorithm is a sequence of functions that takes in n training samples and maps it into a function in the functions class. So here, the capital T refers to either the natural numbers or the non-negative real numbers, depending on whether you are considering discrete algorithms or continuous algorithms. So for any independent identically distributed test sample x, the training algorithm maps it into a real number which is its prediction. When t goes to infinity, if the limit of the training algorithm exists in the L2 sense, we denote this limit by the estimator. So in this way, the estimator is really computed by this training algorithm. The functions class concerned in this video is the class of mean-field neural networks. It consists of all the functions f nu that can be written into this integral. Here sigma is called the activation function, and nu belongs to the set of all the probability measures that are absolutely continuous with respect to the Lévy measure on theta. So theta is somehow a cylindrical. The function f nu can be understood as an infinite width limit of two layers neural network, thanks to the central limit theorem. The advantage of this parameterization is that now the functions class or the statistical model is linearly parameterized, so the analysis of its statistical properties and optimization properties are easier. In the following, for any probability measure nu, we use ρ to denote its probability density function with respect to the Lévy measure, and we denote entropy minus by its negative Shannon entropy. Now we introduce the learning algorithm concerned in this video, the mean-field Langevin dynamics, MFLD. As there exists a correspondence between the probability measures and the functions in the functions class, we only need to specify the sequence of probability measures. We let the initialization of this learning algorithm to be corresponding to the uniform distribution over theta, that is nu0, and we set the learning algorithm at time t corresponds to the probability measure nu-t, whose probability density function ρt satisfies this nonlinear Fokker-Planck equation. Lambda is called the temperature of this system. Here Vt is called the interaction potential. In this video, you are not assumed to have a background on the partial differential equations, so take it easy. Let's draw a picture. This nonlinear Fokker-Planck equation describes the evolution of a sequence of probability measures over this cylindrical. In the initialization point, the probability measure is a uniform distribution over the cylindrical. As the time t goes to infinity, the probability density function becomes concentrating around a certain point. You can also use the nonlinear Mac-Kin-Vlasov equation to write the stochastic differential equation version of this nonlinear Fokker-Planck equation. And then after using the Euler-Maruyama discretization, you get this discretized finite width version of this training algorithm. It's nothing but a projected noisy gradient descent. The geometric meaning of this stochastic differential equation is describing the behavior of interacting particles. The particle is forced simultaneously by the drift provided by the loss function and the diffusion provided by the Gaussian noise. It is known that under some assumptions, the limit of these nonlinear Fokker-Planck equations in the L2 sense exists, and we use it to define our estimator. One beautiful observation is that one can prove that the limit distribution of this equation actually solves this convex optimization problem. The first term in this optimization objective function is the empirical risk, and the second term is lambda times the negative entropy, which provides a regularization. It is easy to see that this optimization problem is convex. Another observation is that actually, this sequence of probability measures is precisely the Wasserstein gradient flow of this regularized empirical risk. In this video, we answered the two central questions of feature learning in the context of MFLD. That is, what features are learned by training the MFLD and why these learned features improved its estimation property, that is, the L2 norm to the square between the estimator produced by MFLD and the signal that we want to estimate. Our answer is based on the fiber-based geometry. To see that, we make some notation. Let's denote alpha W by the pair that is distributed according to the probability measure nu. So here, W is a vector in the Euclidean ball and alpha is in the interval. We also define alpha nu as a function of W that maps it into the conditional expectation only with respect to alpha. The key observation is that the function's class can be decomposed into fiber and base. We denote by phi nu by the law of the random vector W. Then each function in the function's class can be rewritten in the following way. First, you expand the integral and you use the density function. Then you use Fubini to swap the integral. Now you identify the inner integral as the conditional expectation times the marginal distribution. You can pause the video to verify it by yourself. Then we get an equivalent formulation of every function f nu. This introduces the fiber-based decomposition, which I'm going to explain it below. In the following, what I referred to the base is written in green, and what I referred to the fiber is written in yellow. Here the base is the marginal distribution phi, which corresponds to the learned features, whereas the fiber is the function a, which determines how the learned features are used to do estimation. You can make an analog to the polar decomposition to understand the fiber-based decomposition. Suppose you want to represent a function in the function's class, then you can first determine its direction, phi nu, which is precisely the learned features. Then you generate a linear space, which is L square of phi nu. In this direction, you determine your function f nu by determining its length. Now, how does this perspective help answering the two central questions? Regarding the second question, that is, how does the learned features help improving the estimation error of the regression function? We know that the estimation error of the regression function can be decomposed to the approximation error of the regression function and the estimation error of the oracle. For those of you who are not familiar with this concept, you can refer to my previous video on the spectral method. So now let's study the estimation error of the oracle. In a reproducing kernel Hilbert space, the estimation error of the oracle depends on the alignment between the oracle and the integral operator of this kernel. This is established by the feature space decomposition method. For those of you who are not familiar with this method, you can refer to my last video on the spectral method. By the feature space decomposition method, the estimation error of the oracle is often written in the sum of four terms form. Here I am made the approximation error term. Now let's consider the following question. To have a small estimation error to the oracle, what kind of alignment relationship is favorable? It is obvious that we want the projected oracle onto the free subspace to have a small L2 norm to the square. because by the feature space decomposition method, this part is regarded to be a part of the noise. This is precisely the motivation of the following concept, the alignment property of an estimator. It says that once the favorable alignment occurs, an estimator should be able to capture this favorable alignment to achieve a small estimation error. This is related to the geometry in one fiber. This geometry is built by feature space decomposition method because it tells you how does an estimator use existing features to do estimation. Now let's place this alignment property into the base fiber geometry. Let's draw a picture. This is the fiber-based decomposition picture, but drawn in a three-dimensional space. Again, this ball refers to the set of all the probability measures, and phi is one marginal distribution on it. This yellow hyperplane is the L2 of phi, which is precisely the fiber generated at the base point phi. And A is a function in this fiber. Now let's zoom into this yellow hyperplane. Suppose now we are standing on this yellow hyperplane. For the sake of generality, we write the optimal feature space decomposition for a general reproducing kernel Hilbert space. In the initialization, no information regarding the supervised regression problem is given. Therefore, there is no reason to believe that a favorable alignment position already exists. It means that in the initialization, the signal projected onto the free subspace may have a large L2 norm. But what we expect is that during training, the alignment is improved in the sense that the projected oracle onto the free subspace is getting a smaller and smaller L2 norm. So naturally, we expect that our estimator is able to exploit this good alignment to have a small estimation error for this oracle. Before we proceed, let's make a definition for the feature learning property of an estimator in the framework of stats learning theory. As a mathematician, I need a clear definition to proceed. The precise definition is given in the paper. In this video, I only gave some intuitions. This definition is also true for general estimators, not restricted to neural networks. Given an estimator, you associated a rule for generating reproducing Hilbert spaces. We denote key phi and h phi by the kernel function and the corresponding RHS generated by the final estimator. And the first requirement is that the feature kernel has to evolve compared to its initialization one. The second requirement is that the estimator has to admit a fiber-based decomposition. The third requirement is that the approximation error of h phi is reduced. The fourth requirement is that the alignment of the oracle in h phi is improved during training, whereas the last one requires that the favorable alignment can be used by the estimator to reduce the estimation error of the oracle. If all the requirements are satisfied, then we see this estimator has the feature learning property when solving this problem, and we call h phi the learned feature space. That is, it contains all the feature learned by this estimator used for solving this problem. You can pause the video to think a bit. Now we apply this definition to mean field Langevin dynamics. So first we need to give the rule for generating the RHS. We define key phi, the learned kernel function, by this form. This expectation is taken with respect to w hat, which is distributed according to phi lambda hat, which is the marginal distribution of nu lambda hat, the long-time limit of the nonlinear Fokker-Planck equation. Now we draw a picture to see how this definition characterizes the feature learning of mean field Langevin dynamics. Again, we draw the fiber-based decomposition picture. At initialization, nu0 is assumed to be a uniform distribution, so we can draw its marginal distribution phi0 as a base point, and then it generates a fiber, this yellow hyperplane. It is L square of phi0, which we can prove it is isometric to the random feature space H0. We first investigate the approximation error of this random feature space H0. We draw the regression function f star and its projection onto this yellow space in the L2 inner product, which is precisely the oracle GH0. As you can see, the projection residue might be large, indicating that the approximation error of this yellow subspace, which is the random feature space, is large. Next, we study the estimation error. Now we zoom into this yellow subspace. This is only related to the oracle. On the random feature space H0, we do its optimal feature space decomposition. As the feature space is random, there is no reason to believe that the oracle is well aligned with the estimation subspace, that is, the red subspace. This may cause a large estimation error. Now let's see the feature dynamics during training. Let's come back to the fiber-based decomposition. Now we run the mean field Langevin dynamics, so the base point phi t, which characterizes which features are learned, will change during time, and consequently, the fiber L square of phi t also changes. Its long-time limit converges to phi infinity, which we denote by phi lambda hat. Also, the fiber on this point is L square of phi lambda hat, which is isometric to each phi, the learned feature space. Now let's see what happened to the approximation error of this learned feature space. Again, we draw the regression function and the oracle. You see that they are rather close to each other, so that the approximation error of the learned feature space is very small. Now we zoom into this learned feature space to see the alignment. What you will see is that after training, the new oracle in the learned feature space is well aligned with the estimation subspace. This is precisely what the definition of feature learning is saying, and one of our objectives is really to verify this definition. One question remains. I know that feature learning may create good alignment, but does the estimator has alignment property so that it can use this good alignment to achieve small estimation error? The answer is yes, and this is precisely what I called the self-regularization property of mean field Langevin dynamics. The intuition behind this proposition is saying that in the learned feature space, the second layer of the mean field Langevin dynamics uses the learned features in the way of a convex regularized empirical risk minimization. Another thing that I don't write on this page is that the regularization function of psi is strongly convex, so that when you analyze the estimation error of this latent estimator Gn hat, you can view it somehow like a ridge regression with regularization parameter lambda. Whatever, it means that this latent estimator really has the alignment property so that it is really able to use the good alignment property to improve the estimation error. I provide one more comment related to the Baron space. We know that the Baron space is maybe the most natural function space to characterize the approximation capability of shallow neural networks. The Baron space also admits a fiber-based decomposition, which is proved by et al. They showed that the Baron space can be written as the union of all the reproducing kernel Hilbert spaces, each phi nu, with the kernel function given by this form. So the feature learning of mean field Langevin dynamics may be viewed as selecting a data-dependent RKHS from this family. Now we come back to the definition of feature learning. The feature kernel evolution is not the main point of this video, and we have seen the fiber-based decomposition of mean field Langevin dynamics, and we have seen the self-regularization property, which proves the alignment property. Now we are left with the third and the fourth point, that is, training really reduces the approximation error and training really improves the alignment. To verify these 2 points, we have to put some assumptions on the problem that we are solving. In this video, let's consider the Gaussian index regression problems. Gaussian index regression problems is a lens of statistical feature learning. This is because in this problem, we assume that the regression function has some low-dimensional structure, and people believe that estimators having the feature learning property should be able to exploit this low-dimensional structure and adapt to that so that it avoids the curse of dimensionality to have a small estimation error. In contrast, for estimators without the feature learning property, it suffers from the curse of dimensionality so that its estimation error is much larger than that of the estimators with feature learning property. So people want to see a separation of estimation errors between the feature learning estimator and non-feature learning estimator in the Gaussian index regression problems. Now let's define this problem. Suppose you have your design vector living in RD. Suppose there exist some unit Euclidean norm vectors W1 star up to Wm star in Rd, so that given the input vector x, the useful information for predicting the output is summarized by the inner product between x and the hidden indices. That is to say, we assume the regression function f star is equal to this formula. Now we train the spherical mean field Langevin dynamics to solve this Gaussian index regression problem. We first focus on the base. Again, let's draw a picture. On the left-hand side, I draw the unit ball of the Euclidean norm in Rd, and I plot the gradient points, which are the hidden indices. Now you initialize your mean field neural network, which has infinite width. So here, the white dots represent the neurons. At initialization, the distribution is the uniform measure, so that the white dots are uniformly distributed over the sphere. Now let's train the neural network. During training, the probability density function of this marginal has formed a multi-spike structure on the sphere, and each spike is located around each hidden indices. This happens when the temperature lambda is of the order O1, which I called the low temperature regime. On the contrary, in the high temperature regime, it is when lambda is of the order omega 1, even though the neurons move, but they cannot form a multi-spike structure, and consequently, the hidden indices are not recovered. It means that this phenomenon has a sharp phase transition around lambda equals theta 1, that is, between the low and high temperature regimes. This is the geometry on the base side, and I call this structure the sea urchin structure because the left-hand side picture looks like a sea urchin. If you are familiar with spin glasses, this might make you remember the Bouvier-Gerhardt localization theorem in the Hope field model. This proposition is saying that you can put a small ball of reduced rho around each hidden index. Then you take as rho as the union of those small balls. Then this proposition tells you that the long-time limit of this nonlinear Fokker-Planck equation put almost no mass outside of S rho. Of course, this holds only in the low temperature regime. This is why I said it is similar to the Bouvier-Gerhardt localization theorem. But here it has some extra statistical properties, because each spike of this sea urchin is located around each hidden index. This sea urchin structure is formed autonomously by the nonlinear Fokker-Planck equation, or if you like, the Wasserstein gradient flow or noisy gradient descent. Another comment is that, if you remember, the long-time limit is solving a regularized empirical risk minimization problem, and the regularization term is given by the negative Shannon entropy. We know that the Shannon entropy penalizes spiky measures, in the sense that the negative Shannon entropy with respect to the big measure of a discrete measure is plus infinite. So this is even more counterintuitive. You have a strong penalty on the spiky measures, but still you get a spiky measure. Next, I'm going to show another proposition, one we only have a single index problem. Suppose that now m equals 1, so that you only have one hidden index. It's called Gaussian single index problem. In this problem, I'm going to show you something that is really interesting. Again, you run your nonlinear Fokker-Planck equation on the sphere, then this proposition is telling you that its long-time limit phi lambda hat has a Lévy-Milman type concentration phenomenon, and this concentration phenomenon depends on the parity of the information exponent of the link function. The information exponent of the link function is defined as the first time when its Hermite coefficient is non-zero. When it is odd, then with high probability with respect to the training samples, the long-time limit of the spherical nonlinear Fokker-Planck equation satisfies the following property. For any one Lipschitz function defined on a sphere, it has the following concentration property, and when it is even, its long-time limit also has this concentration phenomenon, but this time it holds for any one Lipschitz function defined on the real projection space and with respect to the projective metric. To me, this proposition is very interesting because it tells us that The long-time limit of the spherical nonlinear Fokker-Planck equation with random interaction potential functions has a concentration phenomenon, and moreover, this concentration has its statistical meaning. Now let's come back to the feature learning framework. One question is, what does this sea urchin structure help in verifying the 2 points of the definition? The key idea is that even though the function's class f is infinite dimensional, thanks to the sea urchin structure, the really useful part of it is finite dimensional. This is because that sea urchin only has finite spikes, and those spikes only span a finite dimensional space. So we can define another set of functions which we call f-info, because it contains all the informative part of the function's class for solving this Gaussian index problem. Then it's very easy to see that the regression function f star belongs to f-info. Thanks to the sea urchin structure, the space spanned by the spikes of this sea urchin is very close to f-info. So we can use this fact to verify the third point of the definition, that is, the approximation error of the learned feature space is vanishing. For the fourth point, that is, the alignment is improved, we can also prove that, but I'm not going to explain it in this video. I'd like to say this feature learning framework is still under construction, so I will explain this framework in detail in a future paper. Now let's go to the statistical result. Let's see how do these structures produce the final statistical rates. This theorem tells you that in a Gaussian index problem, the spherical mean field Langevin dynamics achieves the min-max optimal rate up to a logarithmic factor. And moreover, in a single index problem, the final convergence rate depends on the information exponent only in a constant way. It means that even though sigma has information index, say 100, the convergence rate is still d over n up to a logarithmic factor, whereas in the kernel regression problems, the convergence rate will be d to the power information index over n. So for those of you who are not familiar with this kind of result, you can refer to my last video about the spectral method. So in summary, in the Gaussian index problems, there really exists a gap between the estimation errors of a feature learning estimator and a non-feature learning estimator. And this is precisely due to the feature learning property of this mean field Langevin dynamics, because we have verified that this mean field Langevin dynamics has the feature learning property when solving the Gaussian index problems. I know you may have a question. Okay, here you assume that the link function is well specified, so the problem is rather easy because you only need to estimate the hidden indices. I would say we already know how to prove the min-max optimality of the mean field Langevin dynamics in general high-dimensional regression problems, but I will not show this in this video. In this video, what I'd like to emphasize is the fiber-based decomposition, the sea urchin structure, the Lévy-Milman type concentration, and the alignment property. So we should view this theorem regarding the Gaussian index problems with well-specified link function as a toy model so that these geometric perspectives are clean and understandable. Now we go to the take-home messages. We've answered the two central questions regarding feature learning in the context of mean field Langevin dynamics. First, the features learned by mean field Langevin dynamics are the features in the learned feature space, and this learned feature space is defined explicitly. Second, it is precisely because the learned feature space has vanishing approximation error and the projection of the regression function onto this learned feature space has good alignment with the estimation subspace, and this good alignment can be captured by a latent estimator with the alignment property thanks to the self-regularization property. So in the end, combining all the above arguments, the feature learning of mean field Langevin dynamics improves its estimation error. In the Gaussian index regression problem, we've seen that the long-time limit of the spherical nonlinear Fokker-Planck equation autonomously form a multi-spike structure, which I called the sea urchin structure, around each hidden index in the low temperature regime. And moreover, in a single index problem, This random probability distribution enjoys a Lévy-Milman type concentration phenomenon depending on the parity of the information exponent. And this low-temperature sea urchin structure form a dimension reduction of the original functions class, so that the effective dimension of this model is of the order MD, so that mean-field Langevin dynamics can achieve the minimax optimal rate for this class of problems. In summary, I've introduced the three layers geometry used to characterize the feature learning of mean-field Langevin dynamics. The first layer is the fiber-based decomposition. The second layer is the sea urchin structure. It tells you what features are learned. While the last layer is the feature space decomposition. It tells you that in the learned feature space, how the learned features are used to improve estimation.